All right. So what I'm going to do today is go through some things that might be on the exam. Um, as you've seen in your assignments, when you take those tests as assignments, a lot of times you'll get the right answer, but the computer doesn't like the way you wrote it. So I have to go in and check that and fix it. So the same thing will happen with this test. So if you don't get, if you think you got something wrong, you may not have. Give me some time to get in there and do that. So I usually do that. These are due Saturday night. I'm usually there Sunday morning working on those. So let me share my screen and we'll get started here. All right, let's start with this one. Okay, what's the voltage across the unknown resistor, R sub X? Anybody?
4.5 volts.
Four and a, 4.5. How'd you come up with that?
Because they're divided proportionally to how much resistance, they're the same, so they each get half.
Okay, yes. So you don't have to do any math on this. The source voltage, this is you happen to know, understand what the characteristics of series and parallel circuits are. And there's several characteristics that are unique to both of them. One of them that's unique to a series circuit is that this source voltage is divided among all of the elements that are in series. This one has two elements, and it's divided not equally, but proportionally. If the two elements or three elements or however many they are, if they are all equal in value, then yes, it'll be divided equally among them. But in this case, we're going to go with this proportionality thing. There's also this voltage divider. It's pretty easy when you see that they're equal. You know that it's going to be, in this case, since there's two of them, it's going to be 50-50. And yeah, half of this is 4.5. Each of them get that. But if you have several resistors and they're not equal, you can use this voltage divider law. And it works like this. To find an unknown voltage, like this one across Rx, voltage across Rx, I can find that by taking this voltage and multiplying it by this over total resistance. So if we look at this, Rx over RT, here is how we find proportionality. We're saying Rx is in this case, 2.7 out of 5.4. But when we set up a proportionality, is it like 1 to 4? Is it like 6 out of 10? What is that relationship of this resistor to all of them? Because once we know that proportionality or that fraction, then we just multiply that fraction by the voltage source, and that gives us the voltage across that resistor. So what's the voltage across this one?
30 volts to RX.
30 volts. How'd you come up with that?
Well, RX has.
Who's speaking?
This is Adam.
Okay.
RX is twice the resistance as the other resistor.
Okay.
When you divide it out proportionally, RX will get 30 volts compared to the 15 that would be left for the 13,000 ohm resistor.
Okay.
What I did is I did 45 times 26 divided by 39 and got 30.
Okay. So in that case, you also set up the proportionality.
I used the formula, yeah.
Yeah. Okay, good. Good. Yeah, we can see this is a 2 to 1. So this has two parts. This has another part. So 3 parts. You divide this by 3. This gets 2 parts of that. This gets the 1 part. So no matter how you do that. So there's another way is I would find the total resistance of this circuit and find the current then, divide the voltage by the resistance to get the current, and then I know what current's flowing through there. And since V is equal to I times R, I would calculate that way. Does everybody see that possibility? All right. What's the voltage across R2 in this one? Should have had the answer by now.
36.
Yeah, 36.
36 because it's in parallel. What's the voltage across the other resistor?
36.
Okay. Because one of the characteristics of parallel circuits is that the source voltage is applied to all the branches. All of these are tied directly to the source. Therefore, all the branches have the same voltage. Right. How much current's going through that washer?
11 amps.
11? Are you sure about that? Anybody disagree? Who said that?
Tom?
Tom, why do you say that?
Because you put the inverse proportional amount of current through the circuit, depending on how much resistance there is. So lower resistance, the more current goes through it. So the washer is twice as much, so it'll get half as much as the dryer. So divide 33 by 3. 11 goes through the washer and 22 goes through the dryer.
It's similar to the relationship we had with the 2-to-1 resistors. I've got the same kind of relationship with this, except as Tom pointed out, the greater current is going to go through the lesser resistance for just kind of common sense reasoning, right? So if we're going to divide this is 2 parts and this is 1 part, divide this by 3, it's 11. So 2 parts will go here and 1 part will go here.
Is there like a formula? I do better with formulas. Is there a formula for this? Okay.
So yeah, using the formula is fine, but don't lose sight on your common sense, things like the greater current's going to go through the lesser resistance, those aspects. All right. How long is this thing going to work till the battery's dead? Here, there's not necessarily a set formula to solve a problem like that. So it has to be done in steps. So if you were faced with this because your boss said, how long is that thing going to run on this battery? Do we need to get a bigger battery? Do we need to do something else? Help me out here. So how would you go about solving this problem?
Calculate how much current is used, like how many amps it would take to run it, divided by how long the battery will last for that many amps.
But in this case, I have a value here, 1200 amp hours. It wants to know how long. So we're talking about hours. So I need to understand that amp hours is amps times hours. You know, this could be 1200 amps for 1 hour. This could be 1 amp for 1200 hours. It could be 600 amps for 2 hours, et cetera, et cetera, et cetera. So if I understand how amp hours works and they're asking for hours, I've got to have more information to solve that. And the information I'm going to have is amps. So to get the amps, I'm going to use Ohm's law. And this gives me 2.4 amps. Now that I have that, and I want to know what the hours are. Well, the hours are the amp hours divided by the amps because the A's cross out and just leave you with the hours. So if I have 1200 amp hours and the current demand on this load is 2.4 amps, I divide this into that and I get 500 hours. In the circuit below, calculate the power consumed by the heating element. So I want to know power. Power is E squared divided by R, E times I, or V times I squared times R. Well, I know R, it's 12K, so I can use this one maybe if I come up with I, or I know R, I could use this one if I can come up with E squared. Do I know the voltage?
You have 2 other resistances that are eating up the voltage, so to speak, before it gets to the heating. Before it gets to the heating element.
Yeah, so to speak, you're right. Yes, in a series circuit, this voltage is divided up proportionally among everything in series. So yes, so that 240 doesn't get there. Most of it does. And if I were a technician, I would probably just go ahead and this is just a practical application. This isn't what you do for your test. For your test, I want exact numbers. But if I were looking at this, I would ballpark it and say there's going to be 240 volts across this. And the reason I'm saying that is because this is 12,000 and these are 77 ohms against 12,000 ohms. These are so insignificant. They're going to have such low drops compared to this one that I would just go ahead and ballpark it based on this. We can use the voltage divider principle right here. And we take, this is 1200 out of a total, or 12,000 out of a total of 12,007. And see, we do get almost all of that voltage across that. And now we have that voltage. I can use the V squared divided by R, and I get 4.74 watts. I could have calculated up the total resistance, divided it into the voltage, and got the current, and then used the I squared times R to get the same thing. So again, you use the method that comes to you first, the one that you're most comfortable with, and that's the right one to use. Oh, this one's a little trickier. Calculate the power consumed by R3. Well, I'm going to have to use Ohm's law again. I mean, this is a more complex problem, and we're going to have to do this in multiple stages. So the first thing I'm going to do, because it's a compound circuit, part of it's in series, part of it's in parallel, I want to have to reduce this to my equivalent circuit so that I can get the total current that's coming out. This voltage divided by the equivalent resistance, that'll give me the current leaving the source, and then I can solve the problem from there. So to do that, first thing I want to do is start over here, furthest away from the battery, and start combining resistors. And I have to combine them according to how they're wired, their configuration. So if I want to combine this one to the next one I get to, which is this one, how are these configured? What wire and configuration are these two resistors?
Those are in series.
Those are in series. So if I'm going to combine them, how do I do that?
It'd just be adding the two, right?
Yes. So now the circuit can be redrawn or rethought of like this. Now I have a 2.4 and it's in parallel to the next one it gets to, which is a 2.4. How do I combine these two?
Do 2.4 times 2.4, and then you would divide it by 4.4.
4.8?
Or 4.8, yeah, sorry. I was
Yeah.
just doing it. I was doing it mentally. I messed up.
Yep, that happens to me. So yeah, that's one way you can do it. You can use the reciprocal thing, like 1 over 2.4 plus 1 over 2.4, and then take the reciprocal of that. But in this particular case, you can also do this. Remember that if you have resistors in parallel, no matter how many you have, but they're all equal, you take the value of one of them and divide it by how many you have to get an equivalent resistance. So no matter which of those methods you used, you would have ended up with this. So now I have a 1.2 and a 3.3. How are they configured?
Series.
So I combine those and I get to this point right here. And now that I'm at this point, I'll use to find the current IT. IT is VT divided by RT. And I get 133.33 milliamps. If I have 133.3 going that way, what happens when it gets to this point? First of all, let me ask you this. If I have 133.3 milliamps and it's going through 3.3K resistor, how much of it comes out the other side?
All of it.
Yeah, all of it, because where can it go? Where can it go? It's like water flowing into a pipe. All the water that enters a pipe exits it, right? So the same thing happens here with this, it's a physical device like a pipe, this physical flow like water, so it behaves the exact same way. Now, all of it gets through, but what happens now at this junction?
It splits proportionally.
It splits proportionally. It doesn't all go the path of least resistance. It doesn't divide equally unless the branches are equally, but the rule is it divides actually inversely proportionally so that the most will go to the smallest branch. So in this case, how much goes one way, how much goes the other?
Half goes to each.
In this case, half goes to each. If I did my calculations right, that's how much should be flowing in that branch. So now that I have a current, I can use I squared R to solve for that. Okay, so in this case, the power company charges me 9 cents per kilowatt hour. How much is it going to cost me to run this thing for 12 hours? This is another practical application. And, you know, we're using these schematics, but this very easily a customer or a client or a boss could come to you and say, look, I've got this heater we need to put out here to heat this plastic up, and we're going to have to run that for 12 hours. How much is that going to cost us to do that? And you're going to have, because they hired you to do this kind of stuff, you're their technician, you're going to have to come up with an answer. So how would you go about doing that? How much is it going to cost to do this?
$1.24.
I don't know. How did you go about getting there?
I calculated watts.
How'd you do that?
Ohm's law, power equals voltage squared over resistance. So 240 squared divided by 50.
Okay.
It gives me 1,152 watts, or 1.15 kilowatts.
Okay.
And then times 12 to give you 12 hours.
Okay.
824. And then times 0.09 cents. $1.24.
Everybody see that? All right, so in addition to what we've been talking about so far, make sure you understand electromagnets, how they're created, what they're used for, some common applications, that kind of stuff. And those characteristics that we were talking about with series and current, or series and parallel circuits, in terms of voltage and currents, how are they alike? How are they different? I'll need you to discuss that. And be specific. Use volts and amps and watts, and make sure you use things right. Like, say the current flows through stuff. Voltage does not go through stuff. Voltage is across 2 points, a measurement between 2 points. Like if you're measuring the length of a table, you're going across the table to see the difference from one end to the other. It's nothing flowing through the table. And also power sources in series and parallel, like batteries. How does that work when you put batteries in series, batteries in parallel, in terms of currents and voltages? And then finally, if you had a circuit and you took measurements with your voltmeter, multimeter, and you tested from point A to C, and this is the reading that you got. You tested from B to D, this is your reading. Based on your testing and getting these results, Is this fuse good or bad? That's what you need to be able to do. And to do that, you have to understand voltage across open circuits, voltage across short circuits, current going through open circuits, current going through short circuits. Those are characteristics of faults. Just about the only kind of fault you're ever going to have in an electrical circuit. It's either going to be short circuit or open circuit. You can't see them a lot of times. You have to be able to find them using measurements. And so that's the purpose of this. I used a meter to obtain measurements, and now I've got to analyze my results to tell me what the situation is. Anybody want to give a shot at this? Just fuse good or bad?
I'd say,
Just
You
the
got 50.
AD tells you that it's bad,
I'd
right?
say,
Yeah, because, well, I think it's bad because B to C has 0 volt.
I think it's good because if you go to A to C, you get 480.
No, so A to B is just across the fuse. If
Yeah.
the fuse is good, then that should read 0 because the voltage is the difference across 2 points. So those would be electrically common. But the fact that A to B is different, that it's 480 volts, shows you that voltage isn't flowing through that fuse.
Current's not
flowing. Sorry,
All right.
current's not flowing, and there is voltage across A to B.
Yeah. So I heard, and also I heard that A to C was reading, but A to C is right across the battery. So, you know, that doesn't really have anything to do with this. I heard A to D was A to D was 0. No, A to D was
It was B to C.
B to C. Yeah, is 0.
That's what I was reading.
Yeah. So that's another indication. What would so A to D, how's it 480 with a blown fuse? A to D.
It's just like measuring it across the battery.
Yeah,
It is.
because it's still negative.
Point D is exactly the same point as point C, right? So, which is right across the battery. Good. So if I give you a chart like this, obviously it's not going to be this chart. Obviously the things on the test aren't going to be anything like what we just did. Oh, there'll be something like it, but not exactly. You'll need to make the thing like, is the bulb burn out? If I give you this list, is the bulb burn out? Is the fuse good? Is the battery dead? Things like that. You'll have to draw a conclusion based on measurements that you're provided that we assume that you took on your own.
Can I ask a question though about this?
Yes, of course.
B to D is reading 0. Does that mean there's no resistance in that bulb?
I'm not reading resistance. No, it doesn't mean that. It means there's no difference in voltage from here to here. You know, you're thinking, well, if there were resistance here, there would be a voltage drop here, right? Is that where you're coming from?
Yes.
Except there's
But
no
there's
current.
no voltage coming into it, right?
There's no current coming
No
into
current
it.
coming into
So
it.
if there's
Sorry.
no current flowing through it, no voltage can develop.
Got it.
Okay. All right. That's it.